Okay, on to problem number 8. So this is assembly to C and C to assembly. So this is just testing your knowledge of both languages and how they interoperate and how they look compared to each other. So the first question is convert the following C code to assembly, and it's a function test and set that takes a volatile unsigned int star value, so an address of a value, and tries to set that value if the value is equal to 0. So if the value is equal to 0, it sets it to 1. So it does dereferences to basically change the value, not the address. So I'm going to write test and set as a procedure. I'm going to assume the value is in R1 as an argument, so I make some assumption about where I'm putting that value. I can assume here, from the previous problem, this is anywhere from R0 to R3. That's kind of the calling convention of the language. It's going to be sort of up to the developers to agree on those semantics. So I'm assuming it's in R1. You can make an assumption like this on the exam as well, as long as you tell me that that's what you're assuming. So here, LDR, we're loading the value, or we're basically loading from the address in R1 into R2. So I'm going to get the actual data value. That's going to allow me to test if it's 0. So that's essentially the same as that star value. So star value is a load when it's in a comparison or when it's on the right-hand side of an equal sign. If it's on the left-hand side, that's a store. So a load to get the value from that gives me an unsigned int instead of an unsigned int star. And then I can do a TEQ. This is a test for equality to see if what's in R2 is the same as 0. If it's not equal, I'm done. I just exit the function, right? Because I'm only doing something if it is equal. If it is equal, then I fall through to this, and I move R2, make the value in R2 1, and then I store that 1 into the address R1, which R1 is the same as value here. So again, that's that star value equals 1. Star value on the left-hand side is a store instruction, and so that stores it into that memory. And then the end BXLR is just getting back to my main function, so whatever called this. So that's it there. So part B, implement a function that counts leading ones in C. So we have functions or we have instructions in assembly that can do this for us, but in C we don't have this, so we have to do something else to do it. So I'm just going to write this as a for loop. So I have an unsigned int input, which is a 32-bit integer, which means that I can do something to each bit of that integer. So if I count from 31 down to 0, that's going to be 32 bits, all 32 bits. And I'm going to do this sort of in reverse because I want to know the leading ones, which are like the ones on the leftmost side of that number. Then I do if not input ANDed with 1 shifted by C. So for C equals 31, this is going to be input ANDed with 1 shifted by 31. So that just gets me the leftmost bit. I'm trying to count leading ones. So if that bit is a 1, input AND 1 shifted by C is going to give me a 1 in the 31st position and then a bunch of zeros, which is a non-zero value. So that's going to be true in C. If I logical not it, that true is going to turn into a false. So basically, if that bit is a 1, I'm going to skip that break, which would otherwise exit my loop and return the total. And I'm going to just go and do the total plus plus. If that bit is a 0, then this is going to give me, the inner part is going to give me a 0, and the logical not is going to end up giving me a true. And then break is going to exit the for loop, and that's going to return the total immediately. We could also just say, return total here instead of break. If you'd rather do it that way. But essentially, we want to early exit the loop as soon as we see a 0, since we're trying to count the leading ones, which is the number of ones before we see a 0. So that's it for that one.